All right, thank you, Clement. Thank you all the organizers for what has so far been very smoothly run summer school. My name is Chris Heunen. I'm fairly tall, short, dark hair, mustache. I go by he, him. I come from the University of Edinburgh, and I'm going to tell you about category theory. Now, category theory is a fairly old and venerable subject. I'm going to be quite ambitious and push through it at a pace because, like Connor, I know some people in the room are fairly expert at it, but some others might be total beginners, and I'm going to try and keep everybody with me. So do please interrupt if anything is unclear, but if it's like subtle and a bit too subtle, I'm going to stick with the basics, so leave it for the coffee break, please. All right. The plan for today is it's going to be in 3 parts. Today, we're going to start at the very beginning. What is a category? What is a functor? And we're going to walk up to something like lambda calculus that we were just seeing and Cartesian closed categories. So the focus of the first hour and a half is going to be universal properties. Then later in the afternoon, I have a master plan here, you see. Later in the afternoon, we're going to talk about monads, because I reckon that's something programmers need to know about. And then tomorrow, we'll go into a bit more detail about monads and some monoidal categories. So that's the plan. So first of all, what's the point of category theory? Why might you be interested in this in the first place? So category theory is a bit of a funny subject. It's different from other parts of maths and maybe even some parts of computer science, in that you try to study objects not by looking at the objects themselves, but how they interact with each other. So it's a bit like, let me start writing now. So the idea is, if you think about the objects that you want to study as people, we're not going to pry open their brains like a neurosurgeon to see what makes them tick inside. We're going to see how they talk to each other, more like a sociologist or a psychologist. We want to see just how they behave. So it's like...
You could raise the desk, by the way.
Aha, that would be brilliant. How do you do that?
Let me check. There should be a button here.
Ooh. Yeah, this is nice. That will be nice. I'm not as tall as you.
But no slouching in the front row.
Yes. I feel more of a distance between us now, though. Okay, so it's all about how objects interact and seeing how objects behave. That makes it ideal for something like semantics, because we do know to some extent how computers behave, but we don't really care how it's implemented. We want to see sort of extensionally, in denotational semantics at least, how, what they do and prove stuff about them. And there's a nice link to logic as well. And the third point I'm going to emphasize is it's in some sense a sort of supporting discipline, in the sense that it's more of a thing to guide your way of thinking. At the end of the day, when you prove something about, categorically prove something about some computer science system, you pretty much can always cut out the category theory if you wanted to. But that's not a nice thing to do. So let me write down, it's sort of a way of thinking, and it guides questions. All right, so that's the rough idea. Oh, sorry, one fourth point is, and this is for people coming from a mathematical angle, category theory is very good at relating different kinds of systems of objects to behave in the same way. So if you were a mathematician, for example, you might be interested in studying, let's say, topological spaces or manifolds or some geometric thing. You know a lot about, let's say, some algebra like groups. You can look at the topological spaces, recognize some of these patterns over here, sort of translate stuff over here, and then calculate stuff over there to prove something over here. You can translate stuff back and forth between fields. That's what categories are very good at. All right, that's enough setup. What actually is a category? A category consists of some pieces of data, and they have to satisfy some axioms. Pieces of data are a collection of objects. That'll typically write A, B, C, capital letters at the front of the Latin alphabet. For every 2 objects, a morphism, a collection of morphisms. Let's say F, G, H. And I'll write going from A to B for every two objects. A and B. All right, so I have a bunch of things, and we have things going between the objects. And the key thing is that I want to be able to compose those things. So for every three objects, so if F is a morphism from A to B, and G is a morphism from B to C, I want there to exist a third morphism that goes straight away from A to C while cutting out the middleman. So this is still part of the data. If you have that, then there is a morphism from A to C. And I'll write it as G circle F. G after F. First to F, then to G. And before I get to the axioms, there's one last piece of data that goes into the definition, which is I want a morphism that does nothing. So for every object A morphism, special morphism that I'll call identity on A, and it goes from A to itself. Okay, so that's all the data we need. A bunch of objects. For every two objects, a bunch of maps, morphisms, or arrows between them, a way to compose them, and some sort of morphism that does nothing. Let me codify what I mean by all that in the axioms, such that there's only two. There's an associativity condition saying that if I have three morphisms going from A to B, from B to C, and from C to D, I can compose them in two ways, right? Let's call them F, G, and H. I can first do F, compose that with G. That gives me a new morphism from A to C. And I can compose that with H, right? And this gives me morphism from A to D. But I could have done another thing. I could have first composed H and G, and then composed that with F. It's also morphism from A to D. And this is a theme we're going to be seeing a lot. There's sort of two standard canonical ways to get from one object to the other. We're just going to insist that they're equal, literally equal. That's the associativity law. And similarly, there's an identity law that says that these special morphisms IDA are actually behaving as identities. So for every morphism F, going from A to B, that's the same as first doing the identity morphism on A and then doing F. And it's also the same as first doing F and then doing the identity on B. For every F going from A to B. That's it. That's the definition of a category. Everybody happy with that? Then the next thing I'm going to do, I'm going to give you a whole load of examples. Okay, example number one is the prototypical one with the objects. This category is called set. Or I have to tell you what the objects are, I have to tell you what the morphisms are, I have to tell you how to compose things. And I'll officially have to prove that they satisfy the associativity law and the identity law. So for the objects, I'm going to take sets. Any set whatsoever will do. And for the morphisms or the arrows going from a set A to set B, I'm going to allow any function, like set theoretical function from A to B. Let's say I'm calling F and G. Now I claim this is a category, because of course, if I have a function from A to B and a function from B to C, I can make a function from A to C, right? By just feeding an element from A into the first function and feeding the result into the second function and getting an element of the third of C. And there's an identity function that just takes an element from A and returns that very element. Nothing much to see here, but it is the prototypical example of a category. And many other categories sort of follow this form. Objects are some sort of sets with some sort of structure, and morphisms are some sort of functions that preserve that structure. So a second example is a slightly different kind of thing. This is called rel. The objects are still sets, but this time the arrows from A to B are going to be relations.
from A to B, by which I mean a subset of A times B. And I prepared something ahead of time for that, so I don't need to spend a lot of time in drawing stuff. Oh no, like that. And you can think about it this kind of way. If I have a set A, let's say it has 3 elements, and I have a set B, let's say it has 4 elements, what does a subset R of A times B mean? It sort of says this element over here is related to that element over there. But for example, this element over here is not related to that element over there. So sort of a graph, bipartite graph like this. And this sort of tells you the intuition of how I'm going to compose 2 such relations. Namely, if I have one from A to B and another one from B to C, I can just, extend the paths. Yeah? Hang on, where did the microphone go?
Oh.
Here in the second case, the morphisms are also sets, right?
Yes, R itself is a set.
Yeah.
That's correct. Oh, that was an easy question.
And I was saying, if you have another relation that's typically written with an arrow with a dash through it, let's say S, to let's say a 2-point thing, let's say it's just something like that, then you can sort of guess what the composition of the 2 is going to be. Namely, we're going to say S after R is all the pairs AC, such that there exists something in the middle that connects them. So A, B have to be in the first relation and B, C have to be in the second relation.
That makes sense? Now it's a little exercise to prove that this is actually associative, that there is something like an identity morphism. So in fact, this S over here is, let me make C a bit bigger. This is actually the identity on C. Because if I compose, I have to connect the others too. Thanks. Like that. So if I take this relation, that's sort of, I can't point on the other screen. This relation over here, if I compose it with anything, it's not going to change that other relation because it doesn't really do anything. It connects that thing to itself and nothing else. And similarly, you can have other variations on set. So here you take all relations, and functions sit inside there. Functions are typical kinds of relations where, for example, this is not allowed, but one element goes to 2 others. And another thing that's not allowed is this element goes nowhere. For a function, a relation is a function exactly when each element of the domain goes to some element of the codomain and only one element of the codomain. So set sits inside of rel in some sense. And you can have other things inside of rel. For example, you can have an example that we might run into later where objects are still sets, but now arrows are partial functions that some people write like that. And again, you can compose partial functions, and there's something like an identity morphism for partial functions. All right? So that's one typical kind of example. Why does it keep doing that? Third example is slightly different. If you give me your favorite partially ordered set, let's say P with less equal is a partially ordered set. Then I can make a category out of this, where the objects are going to be the elements of P. And I'm going to put exactly one morphism. The arrows are going to be, there's going to be an arrow from P to Q, if and only if P is less equal Q. So for example, if your post set is, what's your favorite post set? Yes, pick an easy one, please. Ah, too difficult. Simpler post set, please.
Power set of a 3 element.
Power set of a 3-element set, that I can draw. So here's
let's call them A, B, C, empty, A, B, C, A, B, A, C, B, A, and that's it, right? So it looks a bit like this.
Is it BC on the right?
Yes, thank you. Did I miss anything? Is that it? So this is the ASA diagram of the pole set. You can make this into a category by just saying, I'm going to make these things into arrows. Like that. And of course, I have to add some arrows because what you're not drawing in the ASA diagram is that the pole set, that partial order is transitive. So if there's an arrow, for example, from the empty set to, I can point from the empty set to A and one to AB, then there's also an arrow that goes straight away. So all these kinds of arrows are also in there. And so I could clutter up the whole thing, but I'm not going to. So that's another example of a category that is not of the form sets with some structure and morphisms preserving that structure. And you also, very good point, you have to add these kinds of things because a partially ordered set is reflexive. That I didn't draw in the ASA diagram there. Okay, so you're starting to get a feel for what a category is supposed to be. Example number 4. I'm going to take as objects, and this category is called pole set. I'm going to take as objects any partially ordered set. P, Q, etc. And as morphisms, I'm going to take functions from the one to the other that are monotone, that preserve the partial order. And by monotone, I mean if P is less equal than P prime, then F of P is also less equal than F of P prime. All right, so this follows the pattern of some set with some structure. The morphisms are functions that preserve that structure. So these are two different ways of looking at pole sets. One is like a small category in some sense. I take a single pole set, view that thing as a category. The other one is very big. All pole sets are in there. And they're sort of qualitatively different. All right. Example number 5. That was 5, right? 5. I'm going to do the same kind of thing with a graph that we just did for a pole set. So if you give me a directed graph, let's say G consists of some vertices and some edges. I'm going to make a category out of this by the same kind of trick. I'm going to take as objects the vertices. So every vertex is an object. And I'm going to put an arrow from one vertex to another. So arrows of type V2W are paths in the graph from V2W. What do I mean by that? For example, if this is your graph, I guess I should have rotated that. How do we make that into a category? Let's look at this vertex over here. What are the paths starting here? Well, there's always a path of length 0 that sort of stays over there. We already have a path going from here to here, so I'm not going to draw it again. But there's also a path that starts here and keeps walking, that goes there. Right? So this is also a morphism, goes this way. And I can keep walking one more step. So this from here to here is also a unique path. Similarly, if I start walking at this vertex, I could have the path of length 0. I could have the path of length 1 that we already have. I could make a path of length, 2. And that's all the paths I can make that start there. Similarly, I can make this path, and that's all the paths induced by this graph. Now this thing I claim is a category again.
because I've sort of by construction made it into something where I can compose all the arrows. If there is an arrow from here to here, from there to there, then there's a composed thing that we drew in. There's identity arrows, and they will sort of satisfy associativity and unit law by construction. Now, just so you don't accuse me of cheating, if this was not a simple directed graph, but there were two arrows, and go away, two arrows over here. That still makes sense, right? Because now I'm going to have two paths over here and two paths over here. And you sort of have to give things names to see what all the compositions are, but hopefully that makes sense. And that's it, I think. All right, so for any directed graph, you can make a category out of it. And just as we did for post sets, that was sort of the small version. You can also have a large version of that. Let me call this category graph. The objects are directed graphs. And the arrows, you should be able to guess this by now, are going to be sort of functions that preserve the structure of the graph. So they're going to be, we'll call them graph morphisms, graph homomorphisms. Homomorphisms. So by that I mean an arrow from VE to V prime E prime is a graph homomorphism, by which I mean a function from the vertices of the domain to the vertices of the codomain, such that if VW is an edge in the domain, then F of V and F of W are still an edge in the codomain.
Edge or path?
An edge. The second one would also give a category, but let's take this one just to be definite. But I'm going to reuse this later, and I want edges here. All right. Then I have two more examples that are maybe slightly more related to what Connor was talking about. Yeah. No.
No identity.
Stop. Say again.
I mean, I think Connor's point was that there's no identities here, right?
Yeah, fair point. No, actually there are. Because the identity function, so let me write it down. So for example,
You're right. Talk about that.
does everybody see that? No. So if I take the identity function from V to V, right, that does absolutely nothing. This satisfies the condition for being a graph homomorphism. Because, you know, of course, if VW is an edge in the graph, then VW is an edge in that graph. See it now? Nice. Okay, and then to different types of examples. Any model of the simply typed lambda calculus I can view as a category. And I'm going to be much less subtle about this than Connor was. I'm not going to talk about dependent anything or how the types are set up. I just mean the way you were taught simply typed lambda calculus in, I don't know, 3rd or 4th year undergrad. Objects are going to be types. So any type in the model of the calculus is going to make an object. And what do you think arrows could be? I'm going to take beta, eta equivalence classes. Of terms of type B. So arrows from A to B. Of terms of type B with exactly one free variable of type A. So that's sort of what you think. If you think about a lambda term going from some type A to some type B, this is what you would come up with if you think the same way as I and some others do. So you have some term where you plug in something of type A, and then when you reduce it, you get something of type B. And that's a perfectly well-defined thing. This is associative, and you have identity terms, identity morphisms. And the last example I want to point out, and this is a really subtle one, but I need to point it out, I think. Some people say there's a category called Hask, or sort of where the objects are something like types again. So objects are types, like Haskell types. And the arrows are something like closed expressions, so arrows from A to B are closed Haskell expressions of type A to B. Right? Of course, you can compose two such things, and of course, you can have something like an identity function. But how do you compose them? So I didn't write this down before because it was more or less obvious, but here there's a subtlety. If I give you a Haskell program of type A to B and another Haskell program of type B to C, how do we make one from A to C? You could say G after F, I'm going to define to be sort of lambda x dot the F of G of X. That's the obvious thing to do. Sorry, the G of F of X. And now I have enough brackets. Right, so you take some input, you feed it to your first function, the result you feed to some second function. Perfectly fine. Seems to be associative. But the problem is, what happens when one of the functions is undefined? So if I take the totally undefined function that always diverges, and I, for example, compose it with the identity function that just returns its input. What's this thing gonna do if I feed it like the unit? It's gonna give you the unit. Right, so in other words, if I compose undefined with identity, I get, I do not get undefined. Right, so in other words, this unit law that we had, where did it go? This one is not satisfying now. So it's not a well-defined category as it stands. One way you can try to fix that is to say, I'm going to equate two of these Haskell programs of type A to B when they are extensionally equal for all x of type A. But what does that mean? All right, what does this mean here? Fx equal to gx. And you will need some sort of operational semantics that says, this is how I'm going to implement Haskell, and things are available like that, like the standard Haskell compiler, say, where you can say, this is what the computer actually does, so this is its behavior. If I do this, if I do this, you literally get the same as when you do that. That would be one way out. But that sort of takes away some of the beauty, I would think. Anyway, that's what some people call Hask, and you have to be careful with that. I think there's a question here and a question there.
Yes, so I think that that example of undefined compose with ID, but applied to unit, that's still undefined in Haskell.
I'm bad at thinking on my feet in front of a big board, but I'm pretty sure I copy pasted this off of a post of Connor's, so I'm pointing blame at him.
I mean, I think the problem is that the function itself, undefined compose ID, is not undefined itself.
But exactly. That's exactly what this is saying.
But if you apply to the unit, then both are undefined because you would have G. So you would apply undefined to unit.
I can't hear you myself, sorry. Undefined equals what?
I think undefined composed with ID is equal to lambda x dot undefined, which is not the same as undefined.
Let me write that down so everybody can follow. Is equal to lambda x dot what?
Undefined. And that's not equal to undefined. So
Okay, does everybody agree with that? Because I can't like type check that on the spot. Are we happy? No. Bob, could you explain?
I just mean that Haskell makes a distinction between a function which will be undefined when you apply it and the undefined function itself. So this, the one on the right is bottom, the other one on
Yes.
the left is not bottom. It's a function which is, so if you never apply the one on the left, you won't. For an exception.
That makes sense. Okay, I think most people are nodding. There was another question here.
Like, so the notion of equality between morphisms, I understand it varies from category to category. So like, if you are talking about like sets, then you can think about point-wise equality between the elements of the set. So here in the case of function, so like, I think you are defining like, yeah, so if each of both functions map same element to like same thing, they're equal, but like here the function can also be non-terminating, right? So in that case, like, how do you define the notion of equality between morphisms?
Yeah,
like,
that's exactly the problem. So that's why I need some sort of operational semantics saying this F and this G literally sort of behave the same way. They do the same thing when I execute them. So otherwise you get that problem. All right, let's push on.
One more.
It's a silly question.
There's no such thing.
Why do you take beta eta equivalence clauses and not just,
Oh, because otherwise associativity can go wrong.
okay, I'll think about it. Thanks.
But just for silly reasons, because the variables like are called different things. It's really the same function, but not syntactically so. All right. And I had planned to be slightly ahead of time, so I'm not going to do this, but I am going to tell you about the next chapter. All right, that's all about categories. So as I was saying earlier, part of the point of category theory is that you can translate things between different categories, and that's the next, like, section 2 of a category theory textbook is called functors. So let's have the definition first. If C and D are categories, a functor from C to D, I'll call it capital F, consists again of some data, and it has to satisfy some axioms, as always. What's the data? Consists of, for each object of F, an object F of a, I'm going to use notation and use the in symbol to say it's an object in the category D for each object A in C. So it sends objects to objects. And just like the kind of graph example we had, I want to do something to morphisms too, and it has to respect the types. So I want to have a morphism that I'll call F applied, big F, the functor applied to little f, the morphism of this type in D for each morphism little f from A to B in C. Right, that's the data. It's something that sends objects over here to objects over there, and something that sends a morphism over here to something sort of a matching type over there, a morphism of the matching type over there. And of course, it has to satisfy some properties, namely that it preserves composition and it preserves identity. So if I have two morphisms in C, say little f that goes from A to B, little g that goes from B to C, I can first compose them in C like that, and then translate them over to the other side with the functor. Or I could take little f, map that over to the other side, do the same to little g, and then compose the two on the D side. So these are two ways to do the same thing, kind of. And again, I'm going to just insist that they're literally the same morphism. And similarly, if I start with the identity morphism in C, I apply the functor to it, I want to get the identity morphism of the right type in D. So that's the identity on f of A. That's fairly, if you follow your nose, this is what you would write down as a map from a category to another. All right, let's have some examples. We had the example of a pole set, right? If you remember, it was example number 3. You start with a pole set, you can make that into a category by taking elements and putting a unique morphism from one element to another if the one is less equal to the other. So if P and Q are pole sets, and I have a monotone function from one to the other, then I can regard P and Q as categories, and I can make a functor from the one category to the other category. How should I write this? Regard as category. Let me underline them to make sure to emphasize that they are categories. And you can make a functor. Let me say underlined F maybe. Going from the category, from the pole set P regarded as a category to the pole set Q regarded as a category by literally just doing what you think it should do. So a functor sends objects to objects. So here's an object of the category P is an element of the pole set P. I'm going to send it to whatever the function f did to it, and that's an element of Q, so an object of the category Q. If I have a morphism of the category P, so that means if P is less equal P prime in P, then I want the functor to send that to a morphism in the category Q. So that means I need to have f of P less equal f of P prime. Right, and that's exactly what being a monotone function says. So that maybe went a bit fast. So I'll give you half a minute to look at it in case you want to ask questions about it or talk about it. So the moral of the story is we can take a pole set, regard that thing as a category. And when it goes further than that, you can also take a monotone map between two pole sets and regard that as a functor between the two associated categories. That's like the small example. All right, I guess you've taken that all in, very good. Same kind of thing we can do for graphs. So if I have two directed graphs, say G and G prime, consisting of vertices and edges, directed graphs. Then I can regard those two as categories, as we saw before, by taking the paths in each of the graphs.
And if I have a graph homomorphism f from the one graph to the other, and again, I can regard that, or I can build out of that and regard as a functor from the one category to the other category. How does that work? Well, a functor sends objects to objects, first of all. So what's an object of the category G? It's a vertex in the graph G. Right, so let's say V. Where do I send it? I'm going to send it exactly to the vertex in the other category, F of V. What's a morphism in the category G? Because I have to send morphisms to morphisms. That's what functors do. Well, it's a path. Right, so if I have a path, I don't know, from V1 to V2 up to Vn, that's what a morphism is. I can make a path out of that in the category G prime, right? Because I apply f to each of the vertices along the path. And because f is a graph homomorphism, if there's an edge from V1 to V2, then there's also going to be an edge from f of V1 to f of V2 in the codomain graph. So this is what the functor does. And sort of by construction, it preserves composition. Because if I have a path on this side and I post-compose it with another path, I can first map it over and then compose, or I can first compose and then map it over. It's just a matter of putting another graph, another path over here or over there. It doesn't make a difference. Okay. More fun examples. This is example number 6. So we had the category set. We had the category rel. I can build a functor from one to the other. So I sort of said that set sits inside rel. Right? Every function I can sort of see as a relation. What does this functor do? It takes a set A, just maps it to itself. That's fine. But what does it do to morphisms? If I have a function f from A to B, I have to send it to a relation from A to B. Right? So a subset of A times B. And I'm going to take sort of the graph of that function. And that's now a relation. Right? So any element of the domain A, I'm going to relate exactly to its image under the function f in the codomain B, and to nothing else. So that way I can make functions into graphs, into relations. Now that's a functor because if I compose two functions and you look at the relations that they induce, something like this. So if you have, this is not a function, but imagine it was a function, then of course function composition follows the same pattern. So I can first compose the function. Oops, what did I do? I'll stop touching it. If I first compose the functions and then make the relation out of it, I could equally have made the relations first and then compose them in this way. Right? It's exactly the same thing. So in other words, you can think of taking the graph of a function as a functor from set to rel. So that's a different kind of thing. This is sort of a functor between large categories in some sense. And another functor between large categories that we're going to see goes the other direction. So this, you could call this thing gamma for graph. I can also go from rel to set. So again, I have to map objects to objects and morphisms to morphisms. So this time I take an object in rel, so a set A. I'm not going to send it to the set A itself. I'm going to send it to the power set of A. So I can call this functor the power set functor. And now if you have a relation from A to B, I need to produce a function from the power set of A to the power set of B. Right, what function could we possibly take? So if I take a subset of A, I have to send it to some subset of B. Who has an idea? I'll repeat.
All successors of A. Yeah.
All the successors of A. So I think what you mean is you take all the elements B that are related to something in U. So there exists an A in U such that AB is an R. Right, so successors of something in U. Right. That's a very good idea. Because this actually does make it into a functor. I'll leave that to yourself to check, and you'll just can take it on faith for now. But this is actually a functor. It maps objects to objects, it maps arrows to arrows of the right type, and it preserves composition and identities. All right. So now what we're going to do is take a 3-minute break, because after this we're going to get slightly shift of gears. Because it's a summer school, it's also nice to meet some people. So talk to the person next to you and maybe think about your favorite category, your favorite functor. If there's something you really want to talk about, we could do that in 3 minutes. So. Okay, I'll start writing a bit lower. All right. All right, all right. That's your 3 minutes. Did everybody make a new friend? Yeah, no, yeah, maybe. Very good. Did anybody think about some specific category or some specific functor that they think is very cool and want to share? It's okay if you don't. Oh, yes.
Pre-sheath categories.
Yeah. They are very cool. Let me get back to that in maybe 20 minutes.
The category of lambda calculus terms and contexts.
Let me not get back to that.
Well, my favorite category is the category of order preserving injections.
Yeah, no, that's a good one. That sort of fits this pattern of. We talked about this category post set, and that's a subcategory of it.
I don't know if this is our favorite, but we were just talking about, you have one side of the adjoint here and you can do the other one if you flip the. If you flip the side of it, so that's a cool functor. There's another power set functor.
I know. That is very cool.
The one I like returns the empty sets.
Ah, that's boring. That's not cool. All right, is that enough? Question, all right.
Yeah, question, not a favorite category, but so my high level understanding, right, so far, so I'm very new to this, right? So
Sorry?
functors are translating categories to other categories.
Mhm.
Now, I assume it's fair to say that you cannot translate, a functor does not exist for any two categories. Is that true? So you cannot always translate one category to another. And if that is true, can you give an example?
There do always exist functors from any category to any other, maybe unless they're both empty. But they're not always interesting.
Okay.
So far we've talked about categories and not sort of studied them. So as I was saying in the beginning, it's all about the behavior of objects in categories, and we haven't talked about that. So you can always translate, for example, by doing, if I have some category C and some category D, I can pick an object here, send all objects over here there to that one object, and send any morphism here to the identity map on that object. That will always preserve composition, always preserve identities, but
you get
really
nothing useful out of it.
exactly.
Mm.
So the kind of functors that are interesting don't just preserve composition, but other stuff that we'll talk about now. Yeah, empty is an exception. Let's not talk about that.
Thank you.
And maybe to go back to the very beginning when it's talking about sort of the origins of category theory are in algebraic topology. You have some category of topological spaces, some category of groups. There's a functor from one to the other that preserves not just composition, but exhibits that certain constructions on topological spaces are mirrored by certain constructions on groups. All right. So I promise you to shift gears a bit. Because we're still on the topic of functors. I'm going to make a category that I'll call cat. Objects of this category are categories. Like C and D, etc. Morphisms of this category are going to be functors. Right, so this is sort of one level up. This is sort of category theory taking its own medicine. If it's all about morphisms between things, then why not morphisms between categories? So an arrows from our functors C to D. And once you have this example, we can go back to, I think it was example number 4 in my notes at least. We had the category of pull sets. And now we have this new category cat. We saw how to regard a single pull set as a single category. And I think I wrote it like P maps to P underline. And we also saw that any monotone function between pull sets gives rise to a functor between the associated categories. And I claim this thing itself is a functor. So this is the kind of translation I'm talking about, a sort of coercion in some sense, but you can view any pull set as a category, and this process itself is functorial. And the same kind of thing you can do for the graphs. So pull sets was slightly boring because, you know, you're not adding any structure. That it's still a pull set, it's just dressed up in some sense. But you can do the same thing for the category of graphs and the category of categories. So I can regard any single graph as a category. Let me call this thing path, maybe. Make the path category of the graph G.
And if I have a graph homomorphism, we saw that that gives rise to a functor between the path categories that I'll now hereby rechristen to path of f. And I claim again, this process itself is a functor. So you regard a directed graph as a category. You can regard a graph homomorphism as a functor. And this process preserves composition. All right. So this, if you haven't seen this before, this might spin your head a bit, but don't worry, that's normal. Now, for the last half hour or so, I want to talk about universal properties, and now we'll get more into what you were asking, the behavior within one category, the objects, how do they all relate to each other? No, sorry, I promised not to write on the very top line. Is this okay? I can certainly try, but I might regress, and please remind me. So a universal property is something that category theorists really like because it sort of nails down what an object is by its behavior. So up to isomorphism, which we'll talk about in a minute, it completely characterizes what the object does. It's sort of saying, here's a specification. I don't care what your implementation is. I want sort of the smallest thing that implements that specification. And I'll start with some examples because I don't want to formalize what universal properties mean. We'll do it by example, and then hopefully you'll get the drift. Yes? Sorry, hang on.
Go back to the previous slide.
Yeah.
A stupid question, but
Don't worry.
so the 9, it's a category, right?
Yes.
So how do I understand the like equality between two functors? Like
So two functors are equal when they're literally the same. When they send the same object to the same object and the same morphism to the same morphism.
okay.
So when we define category, I was a bit hazy about, it's a collection of objects, is it a set or not? And I don't
Yeah.
want to get into size issues because there are subtleties there.
Okay.
But you can talk about equality of things.
Okay. Yeah, thanks.
All right, universal properties. So one example of a universal property is something called a terminal object. An object A in some category C is what's called terminal. If for any other object, for any possibly other object, there is a unique morphism from the second one to the first. And let me make this into a different color. This is sort of what universal properties are all about. For some given something something, there exists a unique morphism doing something something. Let me write that down. And it's a fairly simple university property. This just says for any object, there's a unique map into it from any other object. So what might you be thinking about? For example, what categories do we have? We talked about, and sometimes people write exclamation mark for this unique morphism. You don't have to give it a name because there's a unique thing. So they sometimes write exclamation mark. Functional programmers like to write this, so we'll sometimes use that. So for example, in the category of sets and functions, which object might be terminal? So we're looking for a set such that for any other set, there's a unique function into that set. What do we think? The empty set. Okay, let's see. So here's the empty set. If it is to be a terminal object, I can give you any other set. For example, the singleton set. let me write it like this, maybe. And there should be a function, a unique function this way. That's not going to work, right? So empty set is not a terminal object. But it's a good guess, because it is canonical in a different way. Any other guesses? Singleton set. So if I give you any other function, other set B, can we make a function of this type? Well, yes, right? You take any element of B and you have to map it to that single element that we call little a. So not only is there a function, it's automatically unique. So in set, a terminal object is any singleton set is terminal. And this sort of characterizes the singleton set, right? Up to bijection, there's only one singleton set, and it characterizes it in a way that says there's functions into and out of it and how they compose, rather than saying, I'm going to pry it open and look at its elements. In the category rel, for example, do you think there's a terminal object in there? So again, we're looking for a set, but this time a set with the property that there's a unique relation into it from any other set. Sorry, say that again. Now it could be an empty set. Let's see. So we're looking for a relation. I give you another set B. What relation could we make? So a relation is just a subset of B times empty. B times empty is just empty. We are looking for a subset of the empty set. There's only one such thing, right? So R has to be empty, the empty relation. So that's right. So in rel, the empty set is a terminal object. So this is already showing that set and rel are like qualitatively different. So the functors between set and rel that we saw, they have to respect this somehow. That we'll get to more later. How about, yeah, no, I think that's enough examples. Do you get the idea behind terminal objects? Or do we want one more example? One more? Okay, let's do pull sets. Pull sets are nice and easy. So we're looking for a partially ordered set such that there's a unique monotone function into it from any other pull set. I'm going to look at you specifically. What do you think? Oh, sorry, I'm putting you on the spot there.
That's okay. Happy to be wrong. I was gonna take either a singleton post set or an empty post set, is my guess.
Yeah, that's a very good guess. So I give you some other pull set P, and we have to make, let's call this thing A again. We have to make a monotone function of this type. Now we know already there's exactly one function, like set theoretical function of that type. And I claim it's always automatically monotone. So hence there's also a unique post set homomorphic monotone function of this type. So in post set 2, I can just copy paste any singleton. I guess it's a full set now. Right, and the same goes for graphs, and the same goes for lots of other categories where the objects are sets with some structure, but not for rel. So you have to be careful. Okay, that is our first example of a universal properties called a terminal object. And I was saying one of the things we like about universal properties is that they sort of define the object up to what a category theorist would call equal. And for that, I first have to talk about what is a morphism. Let's say F from A to B in a category is called an isomorphism. If there is another morphism going the opposite direction, such that if I first do F and then do G, I get the identity on A, and if I do it the other way around, I get the identity on B. So in other words, G is sort of the inverse of A. I can undo F by doing G either way around. So if we're talking about the category set, for example, the isomorphisms would be bijections, right? Functions that have an inverse, literally. And when an isomorphism exists between two objects A and B, then A and B sort of behave the same. Right, up to this isomorphism, they have the exact same number of morphisms coming in. They compose the exact same way with all morphisms going out, and all functors respect isomorphism. So if I have two objects isomorphic over here, some functor mapping them to a different category, they're still going to be isomorphic over there. Right, because the functor takes the inverse to some morphism and it respects the composition. So that morphism is going to be an inverse over there. Right, so isomorphism is sort of the right way of thinking about two objects being the same. We don't care if they're actually literally the same. We care about whether they behave the same. And once I've done this, I'm going to squeeze this on this slide. Now you can prove that terminal objects are unique up to isomorphism. What do I mean by that? So if I have two objects, A and B, that little proof. If A and B are both terminal, then I claim, so here's A, there's B. B is terminal, so there's a unique map from A to B. That's by definition of B being terminal. I'm not even going to give it a name. But A is also terminal, so there's a unique map from B to A. Right? By definition of A being terminal. Now A is terminal, so there's a unique map from A to A. There's a unique map from A to A. And I already know there is at least one map from A to A, which is the identity map from A to A. So that unique map has to be the identity on A. This is where the unicity comes into play. And the same for B. B is terminal, so there's at least one map, and it's the identity map. So I have at least all of these maps over here. And I claim this is the inverse of that. Because if I first go here and then go there, I get A map from A to A. There's a unique such thing, so it has to be this one. And the same the other way around. So the composition the other way around is also the identity. So these two things are inverses, and A and B are isomorphic. And this is the typical way you will use a universal property, to use this uniqueness in some way. Okay, let's move on. Oh, yes, go ahead.
Just a little thing. In the first definition, you just talk about the uniqueness, and in the lemma on the bottom, you talk about uniqueness up to isomorphism. Do you differ? So is it uniqueness on morphisms, or is it also uniqueness up to isomorphism on morphisms?
So you can, as we mentioned earlier, talk about actual like syntactic equality of objects and of morphisms. That's something that's legal, you can do. But you can also say two objects are isomorphic or not. That's a different kind of reflexive relation, a different kind of equality, if you like. Both exist. Go ahead.
One is equality in the meta theory, and like that. So one is the equality in the meta theory, and the other is the equality, like the notion of equalness within the theory of like category.
Yeah, that's right. That's a fair way of looking at it. So literal equality of morphisms is something sort of in the meta theory that I'm being easy about, is something like set theory if you want. Isomorphism is something I've defined that we can reason about like internally in the theory I'm defining. Does that help? But often isomorphism is the nicer way. That's more useful to a category theorist rather than actual equality. Because again, we want to know when they behave the same, not when they are literally the same implementation of something.
I might have misunderstood the question, but the question is whether in the definition, whether it matters whether we use that there's a unique morphism, or whether there's any way of saying that there's a unique morphism up to isomorphism.
So the second thing doesn't make sense as
Exactly,
it stands.
exactly. It doesn't make sense, at least in this example. Maybe it makes sense if you look at the concept. I don't know.
So I'm going to make a side remark and I want you to immediately forget it. So you can talk about equality of objects. You can talk about equality of morphisms. You could talk about isomorphism of objects. You cannot talk about isomorphism of morphisms. We haven't defined that. Now, there's some people that do define something like that, and then you get into something called higher category theory, where you have not just morphisms between objects, but morphisms between morphisms and on to infinity. But now forget. Yes, let's have some questions.
I just, maybe I was misunderstanding the question, but the way I understood the question was that they were asking if, like, for example, you could have multiple terminal morphisms that are isomorphic, but not strictly equal. So maybe that definition would then be wrong. But I think the answer is actually, well, yeah.
I mean,
And I
this-
think they actually potentially raise a good point, because like, could you have multiple terminal morphisms that are isomorphic to each other, but distinct in a meta-theoretic sense?
So first of all, terminal morphism is not a thing. You can talk about terminal objects, and part of
Yeah.
that definition is there's something to do with morphisms.
Yeah. Well, okay, I'm saying the morphism that identifies the
This
terminal
one?
object. Yeah. Like, you could be in a category, I guess, maybe that has multiple morphisms to the terminal object that are well, actually, no, you couldn't.
No, you cannot.
Yeah. So that answers my own question. But I think the question was about whether or not that unique, the first unique, has to be strictly unique, or whether it should be unique up to isomorphism. And the answer is
Yes.
it should be
So,
strictly. unique.
yes,
That-
let me
that is
emphasize
correct.
this. Make it green. There's only one way to read this, but yes, it's like strictly unique in the equality of the meta theory kind of sense. Does that clear it up for, I think it was you? Yeah. All right, any other questions before we go on? All right, so that was terminal object. Second kind of universal property I want to talk with you about is products. Oops, and I want to go a bit lower. If A and B are objects in some category, C, a product of A and B is another object that I'll call A times B, together with maps going to A and to B that we'll call first and second. And sometimes people write pi for projection or pi A, but we'll go with first and second, such that something happens. And something is this. Okay, so you gave me A and B, two objects. I want to check whether the black stuff is a product or not. what's the property of being a product? If there's any other thing that pretends to be a product, C with two maps to A and B called F and G, and this is where the universal property comes in, then there's a unique map from C to A times B. That's called a tuple of F and G. That makes these two triangles commute. So that means I can sort of reconstruct this pretend projection by first doing the tuple and then the actual projection. And similarly, I can reconstruct G by doing tuple and then second. Right, so let me spell it out further. Maybe I'll make this one green, because this is the universal uniqueness thing. Such that, so this is a bit of a mouthful, for every object C and maps like that, there is unique map from C to A times B, such that, what is it? F equals first after tuple and G equals second after tuple. Right, so I wrote it down in a lot of text, but this diagram is all you really need to remember. So the blue stuff is, hang on, sorry, just a minute. So the blue stuff is what we're checking. Two objects that are given, we want to know if they have a product or not. The black stuff is the product itself. The gray stuff is part of the definition of universal property, some sort of pretend product. The green thing is the unique map. That is like the witness to the universal property. And so there's a lot of quantifiers involved, but that's the idea. So, for example, it's called product for a reason in set. What might be the product of two sets, A and B? I claim, like the Cartesian product of sets, so the set of pairs of elements, is a categorical product. So you give me two sets A and B. I have to give you the black stuff. So here I take the Cartesian product of the sets. Here I take, the function that takes a pair of a little a and a little b and returns little a. And here you return little b, fine functions. And I claim they satisfy this universal property, because if you give me any other set C, any other function f and g, I can make this one. What does it do? It takes an element in here, little c. Well, I know that it has to send it to some tuple of elements, some pair of elements. I know that the first one is going to have to be f of little c. Right? Otherwise, this thing is never going to commute. I also know that the second thing in the pair has to be g of little c. Otherwise, this triangle is never going to commute. So in other words, I have to send little c to, f of c comma g of c, the pair of fc and gc. That's a function. I've defined it. It makes the triangles commute. And I've also argued already that it's the only thing I could have defined to make the triangles commute. So there's a unique such function. Okay, just for fun, we're going to do one more example, which is rel. You think rel has products in this categorical sense? So again, I give you two sets, A and B. I'm asking, can you make the black stuff, but now they're relations rather than functions, such as for each gray stuff, there is green stuff. So first instinct you might have is, okay, let's just take Cartesian product of sets again. Is that going to work? I see some people shaking their heads over there. Why are you shaking your head? I'll shake my head. That's not going to work because sort of the uniqueness of this is gone. I can make this triangle commute in a lot of other ways because now, just because. So we need to find something else. What can we put here instead? And I'll give you a hint. Now we can take the disjoint union of sets. Here's a categorical product. So you give me two sets A and B. I put the disjoint union of sets A and B here. What could be the map that sends a relation between the disjoint union of A and B and A? Well, I relate the pair little a, little b to little a and nothing else. And I can make a relation over here that relates the pair little a, little b to b and nothing else. Now, if you give me any other set C, any other relations F and G, what relation could we put here? Well, if little c relates to some little a, I'm just going to relate it over here too. If little c relates to little b over here, I'm just going to relate it there too. That certainly makes the two triangles commute. If I had related little c to anything else at all, then one of the two triangles would break. Right? Because if I take that extra thing, let's say it's on this side of the sum, then you know that's related to this thing, but it wasn't related over there, so this would not be the same as that. So this universal property is a bit of a tension, right? The existence says this object is sort of big enough to receive stuff, but the uniqueness says it's sort of small enough that there's no extra accidental stuff. And you see it really behaves differently in different categories, right? You might think set and rel are related because they both have sets as objects, but that's not the important bit. The morphisms are much more important than the objects because they determine how things behave. And both of these categories have products, but they're really different things. All right, then in the last 5 minutes, I want to give you one more example of a universal property, and then circle back to lambda calculus. And we can do this in 5 minutes. So the definition of our third kind of universal property is if A and B are objects, an exponential object that's sometimes written b to the power a, is an object such that something unique. And here's the green thing. It's the same kind of thing. I can't point that high. So an exponential object, what would we like it to be? It's something that supports some sort of function evaluation. So the exponential object should be something like functions from A to B. What does that mean? If I feed it an input A, I should be able to get an output B. So for any sort of function from A to B, if you like, I should be able to evaluate it at any type, term, element of A. So that's the data. What's the property? If I have any other pretender that wants to be an exponential object, and it also comes with something that pretends to be an evaluation map, then I can there's a unique thing over here that I can query and put over here. I'm sorry, I have to be rather quick, but this is the universal property. This thing exists uniquely.
So I can write this as like, no, let me not give it a name actually. So in the category of sets and functions, for example, you can literally take the set of functions from A to B, and it will satisfy this universal property. And of course, the evaluation map is going to take an f, it's going to take little a, and it's going to return f of little a. The same kind of thing happens for graphs, sorry, for post sets and graphs as single categories, and for anything that's set with some extra structure. But this is, as you can tell, sort of, I didn't write out the whole in words what all the quantifiers are, because it's slightly more complicated than for products and for terminal objects. And it also behaves more differently. Because in the category of all directed graphs, you might think I'm going to take all the graph homomorphisms from G to A and make that into a graph again somehow. But that's not going to work. So graph does have exponential objects, but they're rather different. They're all the graph homomorphisms from this graph times G to H. So exponential objects do exist, but you can't just follow your set theoretic nulls this time. You really have to work for it. So you have to come up with this definition and check that it satisfies the universal property. And then in 2 minutes, let me finish with saying that a category is what's called Cartesian closed if it has terminal object, a terminal object, all binary products, and all exponential objects. So by that I mean, whenever you give me two objects A and B, in the category there exists a product A times B, and there exists an exponential object B to the power A. So that's called Cartesian closed category. So that's in some sense things that behave a lot like category of sets. And at the very final thing, what I wanted to say, and I just want to mention this, and we're not going to go into details because time is up and we need lunch. You can make a category again out of Cartesian categories. So the objects are Cartesian categories, Cartesian closed categories. The arrows are just functors. I can make a category of models of the simply type lambda calculus. I claim there's functors between these two things. And in fact, if you go up and down, you get an isomorphic category or lambda model of the lambda calculus. So we'll see tomorrow that that means these two categories are equivalent. They sort of behave the same in some sense. So you can really think about Cartesian closed categories as models of the lambda calculus and vice versa. So you can translate anything you know about lambda calculus into things about Cartesian closed categories and calculate stuff there. And now I think it's time to stop. But one more question.
What do you mean by all binary products or all exponentials?
Yes, I'm rushing a bit. Sorry about that. Thank you for calling me out. I mean, for all binary products, it means, for example, if A and B are objects in the category, then they have a product. Then you know A times B exists. And exponential objects also, and B to the power A exists. So in our examples, we saw, for example, set and graph are Cartesian closed, but there are lots of categories that are not Cartesian closed. For example, I think any post set, if you regard it as a category, is hardly ever going to be Cartesian closed, unless it's maybe empty or singleton or something. Any other questions you want to ask now before we go at lunch? If not, then thank you. Enjoy lunch.
Just outside. Enjoy.
Thank you.